So here he's doing one. The University of Sussex is constantly seeking to employ the best possible lecturers, people as lecturers. No, not really. No, really it is. Anyway, that's his university. Anyway, they want to revise a questionnaire based on Bland's theory of research methods lecturers. The theory predicts that good research methods lecturers should have 4 characteristics. A profound love of statistics, enthusiasm for experimental design, a love of teaching, and a complete absence of normal interpersonal skills. These characteristics should be related, that is correlated, to the teaching of statistics for scientific experiments, TOSI. For already existed. Lots of typos in here. The university revised this questionnaire and it became the teaching of statistics for scientific experiments revised, the TOSI-R. They gave this questionnaire to 239 research methods lecturers around the world to see if it supported Bland's theory. Questionnaire is below, and the data are in the TOSI-R's file. Conduct the factor analysis with appropriate rotation. See the factor structure of the data. So here, and these are the questions that are the items, right, for the factor analysis. And you have it's going to be scaled on a 1, 2, 3, 4, 5 scale, or 5, 4, 3, 2, 1 scale. And you can see they're funny questions. I still live with my mother and have little personal hygiene. This is a bad one for stats teachers. Okay, so there are. So there's 28 items. To determine if the correlation matrix was, which is smaller than 0.01, and therefore indicates that multicollinearity could be a problem in these data. Although strictly speaking, because we're using principal components analysis, we don't need to worry. The determinant of the correlation matrix was tiny. So let's see if we show that. Bartlett's test of sphericity would be the test of whether there's enough intercorrelation. Highly significant. Sampling adequacy is high for the CMO, so it looks like we're doing pretty well.
You want that to be high.
You want that to be high? And then the extraction numbers are the communalities. So what are those?
So you want our Bartlett's test to be significant, right?
Yeah.
And you want high numbers for the KML.
Yeah. Otherwise, you don't have enough intercorrelation to conduct the principal components or factor analysis. Things have to be correlated to find them in common, right? Okay, then it gives you the 28 items and the extraction, which is the communality for each of them. So anything that you notice in those?
There's nothing jumping out straight.
Yeah, maybe the helping others to understand sums of squares is a great feeling is a little bit low, meaning that that didn't load in anything very well.
What is this supposed to test?
This is the one where you square the loadings.
No, like this test.
Oh, and this is to test screening for stats teachers, for methods teachers, teachers of measurement, stats, research design.
The highest loading or highest extraction is a quiver with excitement when thinking about designing my next experiment.
Yeah, that doesn't tell you anything about the factor, just that that's used a lot.
Oh, usually.
So these numbers just tell you that these items get used somewhere in the factor analysis.
Okay.
Can you
So-
square them to?
Oh, you don't have to square them. You can just look to see how much. No, these don't get squared. You square the loadings to add to this number. Well, we'll see that again when we look at the actual. Okay, demonstrate that when communalities extraction are above 0.5, a sample size between 100 and 200 can be adequate. Even when communalities are below 0.5, a sample size of 500 should be sufficient. We have 239 with some communalities below 0.5, so sample size may not quite be adequate. However, the KMO measure of sampling adequacy is 0.894, which is above Kaiser's recommendation of 0.5. This value is also meritorious and almost marvelous according to the Hutchin and so and so. As such, the evidence suggests that sample size is adequate to yield distinct reliable factors. Bartlett's test tells us with the correlation between the question is sufficiently large. We said this already. Different from 0. All right, so without any rotation, here are the eigenvalues. Eigenvalues are the loading squared and added up down the columns. And we do it for each component that's tried. So it does it for all 28 items, but we obviously aren't going to have 28 components. So the first component really looks like it dominates. It takes up 32% of the variance, and the next one only adds 9% of the variance more. So maybe we're going to end up with fewer than all of those items. If we use the Kaiser criterion, we'd say let's keep the first 5 items, but we'll look at a Scree test and maybe decide we want to cut it off sooner than that. The one to the right just kept the first 5 because they're above 1. The eigenvalues are above 1. Here's the Scree plot, and you can see how quickly they drop off. So you might justify less than 5 full items, although you can see that it really levels off after 5. So the Scree idea is like, well, once it starts really leveling off, there's no point in putting any more in there. So you could make a judgment between 5, 4, or 3 items probably here would be reasonable. There's no really one right answer to that. You just have to justify what you're doing. Kaiser criteria for retaining factors, like 31. Kaiser criteria is accurate when there are less than 30 variables and the communalities after extraction are greater than 7.7. So the Scree plot shows clear inflections at 3 and 5 factors. So using the Scree plot, you could justify extracting 3 or 5 factors. Then he asked to suppress the low values, and this is the unrotated component matrix. So we can see we're getting clear-cut little clusters here. That's what we want. But we probably don't want to look at this one. We want to look at the rotated one. Should choose an oblique rotation because the question says that the constructs we're measuring are related. I guess so. Looking at the pattern matrix, using loadings greater than 0.4 as recommended by Stevens, we see the following pattern. Factor 1, let's see, did they already rotate it? I don't think so. Factor 3, factor 4, factor, pattern matrix. So let's go ahead and see. Factor 1 seems to relate. Let's look at the actual rotated one. I think it's going to be 7 already. So the first factor is quiver with excitement when thinking about designing my next experiment. I like controlled conditions. I enjoy sitting in the park contemplating whether to use participant observation in my next experiment. Thinking about bone for any corrections gives me a tingly feeling in my groin. Designing experiments is fun. I calculate ANOVAs in my head. All right, so let's see what Factor 2, I like to help students. If I had a big gun, I'd shoot all the students and they have to teach. So notice that's negative. So there's one of those with positive and negative. Teaching others makes me want to swallow a large bottle of bleach. It's also a negative one. Standing in front of 300 people in no way makes me lose control of my bowels. Also negative. I spend lots of time helping students. I love teaching. So that one's clearly something to do with.
This isn't a real test.
No, this whole book is filled with make-believe ones. I still love my mother and have a little personal hygiene. So this is the nerdy one. I spend spare time talking to the pigeons. My cat's my only friend. People fall asleep as soon as I open my mouth. I love teaching students to pretend. So the factors are a lot clearer cut. So he kind of went from the unrotated to the rotated. Factor 1 relates to love of methods and statistics. Factor 2 to the love of teaching. Factor 3 is an absence of normal social skills. This doesn't support the original 4-factor model suggested because the data indicate that love of methods and statistics can be separated. If you love one, you love the other. Can't be separated, you love the other. So you probably tried it with 4 and then you cut down to 3 meaningful ones. Okay. Any other concepts in factor analysis? This was an exploratory, confirmatory. By theory, you set the factors ahead of time. So we took this one and went to the next step and found another 300 to 400 nerdy stats teachers around the world, and then try to use these, try to actually model this particular 3-model system. And it fit really well. Then we would use goodness of fit statistics and stuff like that. If you might have had, like you might want to use these 3 factors in a regression or in a more complicated model. You could have a structure equation model and maybe related to, I don't know what, to, so let's say you use these 3s as outcomes in a structural equation model and did like early attachment history, latent measures, domineering mother latent measures, and social rejection measures. You might fit those together in a structural equation model with all latent measures, showing that the nerdy stats teacher one, especially if they're high in that one, they had overprotective attachment histories and not too many friends or something. Covered the rest of them, I think. Principal components versus factor analysis. Remember, if you see the matrix, the original correlation matrix, there's ones in the diagonal. That's the data being analyzed. That's a principal components analysis. If there's commonalities in the matrix, that's a factor analysis. Principal factor access, or one of the factor analytic ones. Difference is you're using shared variance versus all the variance.
Factor analysis
With commonality. So in factor analysis, you're just taking the shared variance, the amount that people have in common with the other, and dividing that into little clusters. In principal components, we take all the variance and do our best to put them into the clusters. Usually in forming a new test or when you don't know what you're doing, principal components is the most obvious thing to do. If you've got a little more theory, you could try some other more factor analytic stuff. Okay. The next one is, I think it's logistic, is that right? Yeah, chapter 6. Another sparkling example here. Research has shown that lecturers are among the most stressed workers. A researcher wanted to know what exactly it was about being a lecturer that created this stress and subsequent burnout. She took 467 lecturers and administered several questionnaires to them that measured burnout, yes or no, perceived control, high score equal low perceived control, so it's kind of funny. Coping style, high score is low ability to cope with stress. Stress from teaching, high score equal teaching creates a lot of stress for the person. Stress from research means a lot of stress from research. Stress from providing pastoral care. Providing pastoral care creates a lot of stress for the person. Stress indicates that perceived control and coping style are important predictors of this variable. The remaining predictors were measured to see the unique contribution of different aspects, the lecturer's work and burnout work. Okay. Analysis should be done hierarchically because Cooper's model indicates that perceived control and coping style are important predictors of burnout. So these variables should be entered in the first block, just because he's setting up the theory that way. The second block should contain the other variables because we don't know anything about their predictive ability. Should enter them in a stepwise fashion, which is possible. Okay, step 1 is the null model, where nothing is in the, whoops, is this the final model? No, this is the final model. Okay, so this is actually what's listed as step 2 in Logistic. Make sure when you look at the logistic output, it usually puts one in with no variables in the equation first. That means nothing. That's just the base. That's the baseline, sort of. And here we got the chi-square from this step. This is just the first step now. With the first, this is just coping and what's the other one? Coping and perceived control and coping are in the first step alone. And you can see that they did create a significant jump in the -2 log likelihood. So if we would have seen the -2 log likelihood before, it would have been a larger number, and now it's gone down by 165.92 points to give us this number right here, 364.179. Cox and Snell R squared would be R squared equivalence in Nagelkirche. So if that was the case, that would mean that the first block of predictors predicts about 44%, somewhere between 30 and 44% of the variance in burnout, yes or no burnout. Overall model accounts for 29 minus 41% of the variance in burnout, as I said. Overall fit of the model is significant for both. First new variable, okay, overall fit of the model. He didn't put in new variables yet, did he? No. Step 2. Okay, so here's step 2. You can see for that step there was a significant increase. In this case, he just put in one variable at a time, so the block. Did he put in one step? Step 2. No, he didn't. Oh, so what he did is he put them in steps within the block. So you can see all of those are significant in any case. So step 2 got us a bigger Nagelkirche between about 36% and 52%. Now we look at the basic output here. At step 1, we can see that both locus of control and coping and teaching were all highly significant. They had odds ratios of 1.097, or about 10% of the variant, about 10% increase in, so for a 1 unit increase in locus of control, you get about 10% more chance of burning out, I guess of not burning out, because that's why I reversed these. However, we do have one negative one, which is teaching, which is significant. So we would want to go ahead and get the anti-log of 0.083. Somebody do that, because oh yeah, I can do it. Maybe he does it below. I don't know if he does it that way. No. Let's see, there we go. No. Will you do it for me? 1.09. See what I did? I just took that and made it a positive number, made that B weight a positive number, and that gave us a 1.09. So if the odds ratio there, instead of being below 1, would be above 1, Very similar to this one too. The coping means a 1 unit increase in coping gives us about a 14% better chance of not burning out. You know, you put them on a negative scale, so the high numbers mean good things, right? Or low mean bad. High numbers mean bad things. Okay, so we got those, the confidence intervals for those. Then in step 2, everything stays significant, including teaching and pastoral. Again, we have another negative one, so we could change that one around. All these odds ratios are like similar to the ones above, 14, 15%, 1.13 to 1, 1.15 to 1. And he just reprints it down here. Seems as though burnout is significantly predicted by perceived control coping style, stress from teaching and stress from giving pastoral care. Tells us that the perceived control, coping ability, and pastoral care, the relationships are positive. That is, you have to look back at the direction of the scales. Poor perceived control, poor ability to cope with stress and stress from giving pastoral care all predict burnout. However, for teaching, the relationship is the opposite way around. This stress from teaching appears to be a positive thing as it predicts not becoming burned out. Any more logistic ones? There's another example you can look at yourselves in logistic. Don't think there's anything new in there. He didn't put in the Hosmer-Lemshow scales. We know how to look at those though. Oh, in this one he does a classification table though. Let's look at that. So here we have condom use. Let's see what this one is. Next part of the outcome, information about the model after variables perceived, safety, gender, banana. Whoops, sorry. Health psychologists into the research in HIV wanted to know factors that influence condom use with a new partner. The outcome measure was whether condom was used, yes or no. Predictor variables were mainly scales of the condom attitude scale. I think this is a real one. Gender, safety relationship measured out of 5 indicate degree to which the person views the relationship as safe from sexually transmitted disease. Sexual experience and previous, a measure not from the CNS, the variable measures whether or not the couple used a condom in their previous encounter. Self-control, a whole bunch of measures there. Okay. So he puts them in, we can see in the overall model, whoops, block 0, block 1, highly significant. This is the classification table. We got 45 plus 29 hits, a 74% hit rate, 14 errors on this side, 12 on that side. Those are the false negatives, false positives. Goodness of fit test was not significant. That's what we want. We'll show the rest of it. And here's the actual equation. And gender was not significant, but the rest of them were. This one's safety we should reverse. Here we get a 2.560, meaning a 1 unit increase in perceived. Is that perceived safety? Is that what perceived was? Perceived, whatever perceive is, more than doubles the chances of using a condom. Or maybe of not using a condom. Not using a condom. Yeah.
I'll say, think this relationship.
Oh, wait a minute. He put the, oh yeah. Yeah, not using a condom. Yeah, so you got to make sure you see how you put the scale in.
What do you call the XP?
Those are odds ratios.
Odds ratios.
Odds ratios, yeah.
So
Exponent of
for every
B.
unit you go up, the odds are that you'll get 2.5 increase in
Right. For every unit increased in perception, your chances of using a condom go up. Well, I don't know. Is it perceived danger?
It's perceived safety of this relationship. So
What was this? What was the direction? High means, I think he reversed.
I think higher safety of like, I don't think you're dangerous to me.
I know, but
The odds were lower?
yeah, let's see how he did. I think he purposely made these. The measures, a measure out of 5 indicates the degree to which the person views his relationship as safe from sexually transmitted disease. So higher scores mean more safe. Okay, so in this case, the higher the safety score, the more likely they are to use a condom.
And that's not.
No, the more likely they are to use a condom.
Or 2.56% more likely.
Not percent, it would be 56, be 156%, subtract that from 1, or it's 2.56 times more likely. Now, I wonder if he coded using a condom as 1 or as a 0. I mean, you need to know all that. Because I would think perceived safety would make you not use a condom, wouldn't you think?
Well, the odds ratio seems to. Because it's
Perceive, what was the safety one, what was the safety measure?
relationship safety. Degree to which the person views the relationship as safe from STDs.
Oh, yeah, okay. So that was the opposite direction, so this was maybe counterintuitive.
And then if we wanted to get a percentage of that, we would take the 2.56 minus 1 times 11.
Correct.
So higher scores in velocity?
Higher scores means more, no, it means more safety. So the more safe you are, the less likely you were to use a condom. That would make sense for that one. This other one's a little less because the higher you perceive it, the less likely you are to use a condom, right? Or
There's actual safety.
or the more likely you are to use a condom, but it must be the people that perceive the relationship as safe are the types that use condoms, maybe. Could be. Let's see what he says.
Wait, what's the difference between perceived safety and safety?
Well, he said up there, that was up in the top, right? He says, perceive the blah, 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 blah.
The
Perceived
perceived risk.
Perceived risk.
Relationship
And
safety.
safety is the relationship safety. This is a real study, so that was kind of interesting. So let's see. The value of the exponent being perceived indicate that if the value of the perceived risk goes up by 1, then the odds of using a condom also increase. Confidence intervals, blah, 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 can be very confident the value. What's more, because both values are greater than 1, we can also be confident the relationship between the perceived and found the sample is true.
And because safety is negative, they're saying if safety goes down, it leads to an increase in confidence.
Yeah, yeah. But in the, yeah, no, that one makes sense. The perceived one, I could have thought could go either way. Perceived risk. Yeah,
So more risk.
twice as likely, and then they go through some of the other ones. Gender was not significant though, right?
Right.
Yeah, gender's not significant, so you don't want to interpret any that are not significant. There's the classification table. Ones we misclassified are there. And all the other stuff we've gone through already. And in this model, you got a 78% hit rate. Pretty good. So this one, we have previous 1 and previous 2. So if you've used, I don't know what those two are, if you use the condom in previous encounters, those are barely significant, actually. That one's barely significant, but if you, but it still gives you almost a 3-to-1 odds. So if you used it before, which makes some sense, just has a pretty big standard error, I guess. Safety significance, so you have to go the other way with that one. Same thing. Okay. Yeah, you have to know how you coded males and females to know what the gender one means. Test of multicollinearity. Let's see. Can affect parameters or equation are prone. The results of the analysis are shown below. The first table, you can see tolerance values for all the values are close to 1. So we actually just put into a regression to see what the tolerance levels would be. even though he used undichotomous outcome, it's still the tolerance still works the same way. So they all look pretty good. Residuals can be plotted here as well as they can in regression. Anything else on logistic? Sensitivity and specificity, we're okay with those. Okay. Last one is Manova and discriminant analysis. We actually kind of just did Manova, but let's look at the discriminant part of it. What chapter is that? Yeah, 14. Clinical psychologist noticed that several of his manic psychotic patients did chicken impersonations in public. He wondered whether this behavior could be used to diagnose this disorder, and so decided to compare his patient against the normal population. He observed 10 of his patients as they went through a normal day. He also needed to observe 10 of the most normal people he could find. Naturally, he chose to observe lecturers at the University of Sussex. All participants using two dependent variables. First, how many chicken impersonations they did in the streets of Brighton over the course of the day. And second, how good their impersonations were, as scored out of 10 by an independent farmyard noise expert. The data are in the file, check and save. Okay. Testing assumptions, first descriptive statistics. Boxes M was significant. And that's not good. On these data, hence the covariance matrices are not equal and the assumption is broken. However, because the group sizes are equal, we can ignore this test because Pillai's trace should be robust to this violation. Fingers crossed. So Pillai's, remember, is the most robust of the multivariate statistics. So we look at the multivariate for group here, and we get a significant difference between the two groups. Both univariate, no, only univariate in quality, not quantity, is significant. Number of chicken impersonations didn't matter. The quality of them did matter. This is between subjects, tests, it's the same thing we just had. Oh, they're just giving the univariate, sorry, that's easy. Wilkes lambda was significant. Standard canonical discriminant functions, so that kind of tells us those work. This is the centroids, those are like the factor loadings. Centroids for each group confirms that one discriminates two groups because the manic psychotics have a negative coefficient, the Sussex lecturers have a positive one. There won't be a combined groups plot because there's only one variant. Overall, we conclude the manic psychotics are distinguished from the Sussex lecturers in terms of the difference between the patterns. This one is just only 2 dBs. This one's a more real one. Different aspects of psychology improved throughout their degree. It took a sample of first year, second year, third years and gave them 5 tests representing different aspects of psychology. And there we go. So now we get these are the 5 tests by year level. Those are just the descriptive statistics. We can look at boxes M, not quite significant, good news. Next table shows the main table of results. Here we can see that, especially for Roy's, it was highly significant, but for all of them, it was significant. So Palais is significant. That gives us some reassurance. We don't have to worry about the assumption violations. And they did univariate tests, either t-tests or Fs to see. And the two groups were different on none of them, actually. Oh, that's Levine's, so yeah. So no homogeneity violations, that's good. That's the same as we've seen. Here's the univariates. We care about group, 0.099, 0.064, 0.06. So none of these are actually significant, but they all look like they went in the same direction. So here's a case where Manova kind of combined them to give you something that individually you wouldn't get. So the Manova score, thinking of that as a latent variable representing psychology knowledge as a whole, actually did a good job of discriminating year level, whereas experimental didn't quite make it, statistics didn't quite make it, personality didn't quite, nor developmental. So that's makes some sense, right? So we don't need to look at contrast because the univariates were not significant. Instead, we see how the dependent variables interact. We need to carry out discriminant function analysis next. So you put it in with the two functions, and we get the first function seems to be significant, the second one's not. And we look at the first function. These are like the regression weights. And we can see that statistics seems to load real positively, experimental's positive, social are the negative ones. So it's kind of separating out the more quantitative oriented students versus non-quantitative, is how that factor actually worked, even though it worked as a whole. So that could work because even though non-quantitative students might not show much improvement through the year levels, quantitative students would, but the other students might do better in social developmental through those year levels, and they kind of counterbalance, and so it's a latent variable as a whole that kind of shows overall psychology knowledge. What do you think that's meaningful or not? There's the centroids, kind of shows you how that works. Standardized discriminant functions tell us the relative contribution of each variable in variates. Looking at the first variate, it's clear that statistics has the greatest contribution, that's what we just said. The second variates, the variate centroids for each group tells us the variate 1 discriminates the first years from the second and third years from the first, have a negative value, whereas the second and third years have positive values for the first variate. So it kind of tells you the directions. Best illuminated by a combined groups plot. The graph plots the variance scores for each person, grouped according to the year level of their degree. In addition, the group centroids are indicated, which are the average variance scores for each group. The plot for these data confirms that variate 1 discriminates the first years from the subsequent years. Look at the horizontal distance between these centroids. So first year, second year, third year. You can look at just the first years. You can see them going kind of there, that pattern. The second years are kind of scattered in here. Third years are out here. And they're kind of represented by these three means.
Because the second function isn't significant at Kaiser, how much can you really say about it?
Well, not too much. You're just trying to understand the relationship between the two. You probably wouldn't use much of that one. The idea is to try to get the first function and make your conclusions in that one. Okay, so that's discriminant. We did more discriminant stuff, but we just covered those recently. So you should know the output from the discriminant function. I'll give you an output from an actual discriminant, not just a little part here. Path we covered. SEM, what I might give you an SEM is just a structural Amos drawing with the beta weights on them, and the output from the goodness of fit. All, you know, the text output, same thing we just did. And ask you some questions about those. What else? So as in last semester, we'll start with the decision tree, 10 questions written out, we'll go through them, hand those in, put away your stuff, then I'll give you output and a cumulative test, just asking questions about the output, like stuff we just did. And that's it then for that. If you have questions on the project, you actually start working on it by then, you can ask after class, ask myself or the TAs. Remember, we won't go over that specific output, but we'll show you a parallel output if you have questions on how to do it or what it means. Got time for more review if you want to. Yeah, we just did Manova at the beginning today, so I don't know much more about that to go over.
Was meta-analysis?
Oh yeah, meta-analysis, okay, so, but there's not much. It's not on this concept list, is it? I forgot. But you do have a concept list with just a few concepts on it, so. Those mostly can be covered just by effect size. That kind of gets doubled up with effect size. So for meta-analysis, I guess basic things from the slides on meta-analysis, like biasing things, they're pretty basic. There's not very many questions I could ask on that. Can't remember if I might have one or two. Think about it for a minute.
We're not able to review the questions that are wrong in prior tests, right?
Yes, I can give you the TAs and you can go over them. Just have to give us a notice, because I have them in my office, so if you want to do that with the TA. So if you do that, you need to let them know to let me know so I can give them the test, which test you want.
The dose response curve, is that different than the ROC?
Those are ROC curves. Oh yeah, we didn't do ROC curves for logistic. So remember, it's it's sensitivity against false positives. Diagonal line is chance discrimination. The more it follows the y-axis and the above axis, the better it is. Area under the curve gives you the importance, how well it discriminates between two things. And the basic reason for doing it is to get cutoff points, to maximize cutoff points. So there could be things like that, like I could give you situations where missing something is not very important, but finding it is very important. That might influence where you put your cutoff points, right? Or vice versa. So like, sample question would be, a new drug has been found to be effective with mice, however it comes with a 6% mortality rate. We want to test it on human beings because we think it might offer hope for prolonging life in cancer. What should the cutoff be for testing that drug? So you'd want to be really sure it works before you kill 6% of people. Right? right? Because you might save a lot more if it works, but if it doesn't work, you're gonna have a price to pay for it. On the other hand, a new drug is found that has no side effects whatsoever, it's cheap, and it promises to shrink tumors. You might as well use a very loose alpha level, anything, because if it's possible that it works, what's the cost? There's hardly any cost to it. So you can kind of look at those kinds of issues. And those are real life important issues. Luckily, we don't usually have interventions that kill people, even though our IRBs are harder on us than the medical ones. I mean, you can go in the same, you go to an IRB at university, before you there's someone that's going to has a risk of lung punctures, and they say, okay, well, as long as they're consented and they know the risk, that's fine. And then we come in and say, we want to ask them some questions and show them some disturbing pictures. Oh my God, that'll freak them out. You can't do that to people. Don't ask them about sexual stuff that really is going to get people. You can't do that. That happens all the time. Anything else?
Isn't it good way to practice like decision tree stuff, like
Yeah, so
examples of those?
get somebody to take a journal and then just take turns reading the study and seeing if you can figure out what statistic they should have used. I think for you, since you're much newer to it, you just need someone to go over even just very simple examples again and again and again until it starts to go. Everybody else, they've kind of reached their asymptote. Mostly are getting they're starting to.
Yeah, there was one from last semester.
Well, there was a practice one from last semester.
Practice.
Yeah,
I sent them out last week.
you sent out. Yeah, those are helpful. They're a little easier. Those practice ones are a little easier to get. But the ones in the test are easier too because they're kind of written out and simplified. So they're not as hard as actually reading them out of the journal. But that's real life. You got to figure it out that way. There's a bunch of stuff in that Manova packet I gave you that's useful about sample size, unequal sample size. Those questions, I can easily ask questions on those. Study that packet that I gave you on Manova, and actually the book covers it pretty well too.
So, can you go over just real quick each of the assumptions? Homoscedasticity is how much variance,
Okay.
along the
We can do the
regression line.
We can do the Manova assumptions because that's everything.
Perfect.
Okay. So we got the big three, so which is normality, homogeneity, these are the univariate ones, and independence of observation, right? Then we've got multivariate normality and homogeneity of variance covariance matrices. Let's do that one. So multivariate normality, we know that the only way we can really get at that is the Mahalanobis. We'll look for multivariate outliers. Homogeneity of variance covariance matrices, that's the same assumption for discriminant analysis as well as for Manova. So if we did the Manova that we did today, we had the 4 groups: high masculine, high feminine, androgynous, undifferentiated. We had, the measures were neuroticism, locus of control, I forget what else there was. Let's make one of these, one more. What did I do? Anyone remember another measure for that one? Neuroticism, locus of control, and we'll just do attitudes. Attitudes towards housework is one. So let's say there's 3 DVs, 4 levels of the IV, and now we look at the variance covariance matrix within each of those 4. So we look at, we'll call this 1, 2, 3. We look at 1, 2, 3, 1, 2, 3. Variance is here. And covariance is here. And those could be correlation coefficients. You do that for all 4 of those. The assumption is that the pattern of variance, covariance are roughly equal across the 4. The relationship between the DVs doesn't change within each different group. All right. So if I wanted to see that, I could print out a correlation matrix with a split file and just split one for each of those groups if I wanted to see those 4 correlation matrices. All right? Make sense? Okay.
Are there specific tests? What is the specific test for normality? Is there one specific one?
Yeah, so the normality you can have a bunch of them, right? We can have the skewness, where you look at the skewness score on the output divided by its standard error. And that's a z-score. There's one for kurtosis. There's the Kolmogorov-Smirnov tests, Wilks-Shapiro tests. Those are all printed out in SPSS as tests of normality, univariate normality. There are no tests for bivariate or multivariate normality directly. But fortunately or unfortunately, the boxes M is sensitive to violations of normality as well as variance covariance matrices.
Yeah. Boxes kind of take care of everything.
Yeah. Well, it kind of, if it's violated, then you got to track down where it's coming from. If it's not violated, you're in good shape.
Bartlett's test does.
Bartlett's test just tells you whether there's enough correlation among the DVs to be useful.
Okay.
So that would be mostly for factor analysis or Manova. You want correlation among the DVs for Manova too. Or discriminant, you can do that too.
So that's something that I want to go over is what each of the tests, I want to review what each of the tests actually tests.
Which tests?
I'd have to review all of
There's
the
so
tests.
many.
You mean Manova, the Manova ones? No. Well, you mean the different, okay, well, we're doing them as we go. So Levine's is univariate homogeneity. You know that. And this
Homogeneity of variance.
homogeneity of variance, univariate, just for one DV at a time.
And you don't want that to
You don't want that to be significant. Boxes M is the variance covariance matrix one, this one. You don't want that to be significant. Bartlett's is for intercorrelation. You do want that to be significant. The KMO also is whether for factor analysis you want that to be high. It's not a significance one. KMO is tells you whether you've got a factorable matrix, so that should be high. What am I forgetting? There's four significance tests for Manova: Pillais, Roy's, Wilks, Hotellings, and those are significant. Obviously, they're just testing multivariate significance.
You mean
For-
those 4 included?
Those 4, you've got them in 15 different places. It's right in front of you in the output from field. So for me to write it down, it's just just know the difference between them if you want to go back and look. So Pillais is the most robust against violations. That's the unique thing about that one. Pillais. P-I-L-L-A-I-S. Wilks lambda is kind of interesting because it's 1 minus r squared. So it's kind of 1 minus the Wilks lambda is r squared, I should say. The Roy's is unique, as we said before, because of its the first variate only. And Hotellings is kind of very similar to the other ones. So those are some more tests of those. Hotellings is another one that does all the variates. Kind of similar to Wilks and Hotellings are about the same. Usually one significant, the other ones. There's slight differences, and it's complicated what the differences are. So. What other tests we're thinking of? Well, let's keep on going through the assumptions. Maybe we'll come up with some more. Then we want linearity. That is, any time there's more than one DV or a DV and a CV, that we're assuming they're a linear relationship to each other. We have homogeneity for, well, a regression. So that's for Ankova.
And that's the most important one for April.
That is important for Ankova. That one violated is a problem. That's the one where you look at the CV by IV interaction. And that is the case where you do not want that to be significant. That's just a test of the assumption.
Do not want to.
Yeah. So the mistake people make is if I give them an Ankova output, they interpret the assumption output for the real output, and they're the exact opposite, right? So in the assumption output, all you're looking at is the CV by IV interaction, and you don't want it to be significant. If it's not significant, you're good. If it is significant, you got to worry about managing that violation. For the other output, you want the CV to be significant, and you want the group to be significant, whatever the group variable is. So that would be very, very different. Variance covariance matrices, homogeneous regression, linearity. What am I forgetting? Homoscedasticity. That's the assumption of the evenness of the errors. The errors are evenly distributed. So in regression, you have some standardized score here, like studentized or standardized, 0, +1, -1, etc. Here, I like to put in predicted scores. Unstandardized predicted is what I like, but he puts in the standardized one, doesn't matter. And your presumption is that the errors are evenly distributed. Remember what we're looking at here. This is a residual. This is the number that's left over when you take the person's predicted value from that equation we just put up there. You plug in their numbers to that equation. You get a predicted value for that person, for their numbers. When we did age, attractiveness, years modeling, whichever ones we ended up sticking with. So for each model, we would get a predicted income. And then we'd find out their real income. And that residual is what we want to look at. We just put those residuals, instead of as an actual number, we put them as a z-score on that axis. So that tells us how far off were we for each person. Right? The farther away they are from this line, the farther off, the worse we did in our prediction. So our assumption is, first of all, we'd like them to be close to the line, but they not always will be. But we'd like them to be kind of evenly distributed, because if they're not, you've got to wonder what the model's doing. So the violations would look like right? Which means that for people who were predicted to have low scores, low salaries, we hit it right on the button. We made no mistakes at all. As soon as we got to the big salary models, we were way off on them. That actually could happen, right? It could be at very low levels of modeling where people are not really making the big bucks. That maybe those factors are totally the determining factor. When we get to the big time stuff, maybe there's other factors that we don't know about. So there's lots of ways that could go wrong, but that tells us whether the model's working. Those are called specification errors. Specification. So homoscedasticity is evenness of errors.
So like for an income example, they could be, if you're just throwing factors in there, for low income, they would be good predictors, but at the higher incomes, maybe not. Maybe they hired somebody else to do it, and it's a weakness for them or something.
Yeah, maybe at the highest levels that they want more extreme models, might really be, right? You kind of look at those supermodels are kind of freaks of nature, some of them, right? They look good on pictures, but they have unbelievably unrealistic dimensions, some of them, where they're incredibly tall and thin. And maybe at lower levels of modeling, when you're just modeling for the Union Tribune, something that regular dimensions is what you want, or you want a face that looks like people can identify with. Whereas the walkway in Paris, you want these strikingly tall African women that have incredible bone structure, and maybe there's factors we just don't put in the equation that would predict their incomes. Now that would be a problem because you're going to get these big outlier incomes, right? Super millionaires at one end and minimum wage at the other. Probably don't want to do those together. Okay. What else am I forgetting? Multicollinearity. Lack of multicollinearity. Sort of an assumption. So in a lot of these models, the predictors can't be too highly correlated.